Greetings, everyone. I'm recording this as we speak, as it is snowing. So if you hear some extra joy in my voice right now, it's because it's snowing outside, and that's always exciting for any teacher. This particular video is going to talk about how to work through a problem where you have an angled projectile that is launched on level ground. Now, what that means is that on level ground, the start height and the end height are probably going to be the same. All right, and you see in this picture what it kind of means. It just means it's sitting on flat ground. All right. Now, this particular question tells us a few things. It says the water balloon launcher is set up on level ground, so we can say the starting height is 0. It's fired at a 35-degree angle, and it launches balloons with a velocity of 12 meters per second. Okay. Now, that tells me right away I know the launch velocity, I know the launch angle. I want to figure out the maximum height the balloons reach, and I want to know the maximum range or horizontal distance the balloons travel. All right. Now, I've split this question in half because we're going to do the max height first and then find the max range. Now, max height is going to be solved just like any other question I've asked where you look for the max height. All right. Now, it looks a little bit different because when we talked about max height before, sometimes we just talked about things that are just going straight up and then straight back down. And it's pretty easy to visualize where the max height is. When something's launched at an angle, though, it can be a little harder to kind of visualize what's going on with max height. But what I'm going to tell you is that the maximum height is still going to follow the rules that it does for any other question. What that means is that the maximum height is probably going to be right here at the top of the arc. And it means that that is going to be the point where it has the highest y position. That also means that this is the point where its y velocity is 0. Because, again, this is where it starts to change direction, starts to go back down. All right, so VF for the y chart will be 0. It's also in a state of free fall as soon as it leaves the cannon. So the acceleration is negative 9.8 meters per second squared. Now, the last piece of information we need to know is what the starting velocity is. And to figure that out, we have to go back and we have to use our idea about breaking velocity into components. Because this velocity is at an angle, so to make it into something I can actually use, I have to figure out what the y component of the initial velocity is. Okay? Now, that's pretty simple for us because the launch velocity is 12 meters per second and the angle is 35 degrees. So the initial launch velocity in the y direction will be 12 sine of 35 degrees, whatever that happens to be. Okay? Now, once we do that, we know 3 things, and we want to find the 4th, which is delta y. So the equation we want to use is the one that has those 4 things, which is this one right here. All right? Now, once you get to this point, you're just solving for it. So you plug in the numbers that what you know. All right, VF is 0, so put 0 right there. VI, 6.88, just got to square that. Acceleration, negative 9.8, so you plug that in there. And if you go through and you do that, and again, I'll pause for a sec, give you a chance to actually kind of work through that, you will get what the maximum y height is. All right, so what you'll see, and if you're still working, just pause the video once you get your answer, unpause it and you see it. But you should get that the maximum y height, the highest this balloon is going to go into the air, is going to be 2.415 meters. All right. Now, that might seem pretty small, but that's still, honestly, that's about, that's probably about 10, 11, 12 feet in the air. That's still pretty high. But what you've done is you've taken that extra piece of information, the fact that this is an angled projectile, turned it into something that you can use, and then solved it like any other maximum height question that we've talked about. All right. Now, finding maximum range is going to be exactly the same. All right. You are going to follow the exact same process you've done for any question with range. The only issue is that you need to kind of figure out a couple things. All right. So in the x direction, we can actually figure out what VI and VF are as well. All right. Just like we did for VI in the y direction, well, so too we do for the x. So it's going to be 12 cosine of 35 degrees. And again, if you're wondering where that comes from our notes where we talk about breaking things into into components. All right. Now, VF is the same because, remember, in the x direction, the velocity is constant and acceleration is 0. Now, I have something written here because I've already done all the work, but in reality, when we start this, you'll notice you don't know the time of flight. Now, there's a couple ways to find it, but what's important here is that you need to find it. So what we need to do is we need to write a y chart. All right. Now, We talked about this previously. There were kind of two main ways to figure out the time of flight. Okay. One of them is you can just figure out how long it takes to get to the top and then double it. The other thing you can do is you can just literally map out the whole motion. All right. Now, what that will look like is that if I'm using my Y chart, the initial Y velocity is 12 times sine of 35 degrees. And again, that's just the Y launch velocity. All right. If I go the entire path, which is what I'm doing, all right, so if I'm mapping out the entire arc, then the final Y velocity is actually going to be the initial Y velocity, but in the negative direction. All right. And again, if you're not quite sure why that is, go back and look at the chicken worksheet because that'll help you map out exactly why that is. All right. Now, once you've done that, the other piece of the puzzle left in the Y chart is the acceleration. And of course, it's a projectile, and in the Y direction for a projectile, the acceleration is always going to be whatever free fall is, which in this case is negative 9.8 meters per second squared. So I now know three things, and I want to solve for time. So I'm going to use this lovely little formula right here because it has those four things in it. All right, I did a little math beforehand, so I moved the stuff around so I could solve for t. So if you don't mind, pause the video at this point, solve for time. And then unpause it when you're ready. Awesome. Okay, so I hope you had a chance to kind of go through and solve for the time. And oh my gosh, there's nothing better than watching your yard slowly start to get covered in snow because it tells you that it's going to start sticking. All right, so the time of flight, if you go through and you plug in all the numbers and you do the calculations correctly, is going to be 1.4 seconds. And that is not an S, or that's not a 5, that is an S. All right, and I can understand immediately why if you look at it, you think that's a 5, but it's not. This should be 1.45 seconds. All right. Now, once you know the time of flight, you can now plug into the X chart and you can solve for what you want. Because if you know the time of flight, you now can plug in and figure out how far it goes. All right. Now, this might seem pretty short, and I understand if you're like, well, 1.4 seconds is not a lot of time. And what I'll tell you is that if you are stuck or you're like, I really don't believe this is the answer, go into that simulator we used in the lab and replicate the question. That is going to let you see very quickly if your answer is right or wrong. So again, I highly recommend if you don't really believe your answer, you're not sure if it's right, put it in the simulator. You can pretty much simulate just about everything we talk about if we're just doing launches. Okay? Now, with that being said, I know the time of flight. I know the X velocity. I'm going to use this formula. Now, if you're wondering why this looks different than one of the kinematic formulas, it's because VI and VF are the same, so you can actually simplify them and just use this lovely little formula that says, my X displacement is just my constant velocity times the time I'm going at. All right, this is pulling from way back. We talked about this kind of the first unit we went through. I know Vx. It's going to be 12 cosine of 35 degrees, which is going to be 9.83 meters per second. T is 1.4 seconds. So take a moment, just kind of wrap up your calculation, and then we'll kind of reveal the final answer. All right, so if you had a chance to kind of go through and calculate that final answer, you'll see that the maximum range this travels is about 13.76 meters. All right. Now, this is the standard way to kind of break down a question where I am launching an object on level ground. All right. You're going to break it into components, you're going to plug it into the charts, and you're going to kind of map out things like maybe maximum height or maximum range and figure out the time of flight based off of those particular positions, those particular things we're looking for. All right. Now, this is the end of this first video because this is kind of a very specific type of projectile problem. The next video is going to be a little bit longer. All right. But it's going to focus on how you solve a problem when the projectile launcher you're focusing on is not on level ground. All right. And I'm going to tell you, it's the most fun video of the year in terms of solving problems. You might disagree, but that's all right because I'm a teacher, so I get to say what's fun and what's not in here. Okay. So with that being said, if you have any questions, of course, come to office hours, shoot me an email, and you can head on to the next video.